Hello guys, welcome back to Mason African Motives. Still on our revisions. This is for Industrial Electronics N4, that is August 2023 exam that we are going to focus on, which was written on the 7th of August 2023. So we're not gonna waste much time. We're just gonna quickly rush through the questions, question paper, so that we see are we supposed to attempt such typical questions. It's very, very important that you do understand your instructions and information, which is, in this case, the most important part. The numbering part is supposed to be clear. Everything that you're doing is supposed to be clear, and each question, as we are given, start each section on a new page, which is a question that you're answering should be on a new page. All right, that one, which it's something that you are supposed to understand and also maintain. I see some of the guys, when answering, they do mix questions. This is question. You're not supposed to do that. Answer each question separately and starting the question on a separate part. So like I said, this is August 2023 exam. But before we start this question or to answer this question paper, I just want to thank those who are part of the membership, who have made us to be able to have this video on the exam of August 2023. So this is something that you can also be part of. So I just want to take you through so that you can see what I'm trying to say. You can join the membership of our channel. This is Mason African Motives. So I'm just gonna have here at Mason. All right, that's at Mason African Motives, so that you can be able to join the membership, so that it allows us to work with more content and more videos for you guys to revise towards your examinations. So this is what you're gonna have here. As you can see here, there is this section which is for members only videos. This section here, it allows you to play the videos which are there for industrial electronics N4, as you can see, the videos that are there, and mathematics N4, which is a token of thanks to our members which are part of the family. So you can just be part of the members by clicking this join here. You can just have this join. It gives you straight to the basic, medium, the approach of gigantic, the ultimate, and also the all-in-one. All right, so these are like the ones that you can join depending with amount that is there. The basic also with amount, everything you can check and you can see which one is best for your budget. So that is it. Or you can just click any video on our members video here. By just clicking any video, it can take you through. As you can see, I cannot play this because this account here is not part of the members. So meaning to say, I can't have this part. I cannot have access to this video unless I become a member. So that is what I'm trying to say. So if you go there or the join, you can also join from there. Then it gives you the steps to become a member. Then you can join with any of those listed levels that are there. And from those levels, you just have to follow. I think just okay to have your everything at the end. You're just gonna able to follow the steps and so forth and so forth, which is there are clear steps there. I don't think it's gonna be difficult for you guys. So that is it, guys, and I want to thank you guys for being part of the subscribers, being 20.4. Thank you for that, and also for supporting our second channel, which is at Medzone TV. So let us also subscribe there so that we can bring content as much as we can. So just go there and subscribe, and very soon we shall be uploading content from there. So like I said, guys, I do not want to waste your time, but I've taken at least some of your time there. All right, question number one, we are given, explain the steps to apply in the following theorems. All right, so that was a basic question. You're supposed to know your superposition theorem, 3 marks. They're saying you're supposed to explain the steps that you take when calculating current. Remember, you'll be calculating currents from any of these. So for the superposition, it follows that we are going to have, all right, let me just show you this part here. We are going to replace all the voltage sources but one with a short circuit in terms of you are given a network with many voltage, with the many resistors that you're going to have, and you've got 2 voltage sources that you are working with. So given a condition that you're working with 2 voltage sources, you're going to short one and you work with one of the voltage source. I think I also explained that from the previous video that I made. Just also try to check there. I explained some of how you can also present this. All right. So that is the first step that you're gonna have. So what you do is that at this stage, when you are calculating or when you're dealing with the voltage sources, when you replace all the voltage source but short circuit one, you are going to calculate depending with what is following you using your Ohm's law and so forth. You're going back to the normal circuit that you are given. You calculate the currents that are flowing. Then you're going to do the same thing, what you did on the first step here, but now you are exchanging to say the first one that you had to short, now you're going to bring it back, you short the other one. So these are the steps that you're given. Then algebraically add all the currents that are taken from step 2 to determine the resultant current across the load. So we are going to have what we calculated in the first place, the currents, then we superimpose our circuit. So it's actually to superimpose our circuit to determine that final current. It means we are simply superimposing. So that is to superimpose the circuit, all right? So that it gives us the current, which is the current across the load in this case, or the current across the resistor that you are working with. So these are the steps that you're going to simply have. And like I said, just try to watch that video so that at least you can add more of this information. But I think this one is a straightforward part. 1.12 we are given for Thevenin's theorem. What are the steps that you are supposed to follow? Remember, for the Thevenin, we must be considering the calculation of VThev, the calculation of RThev, but on which conditions are you going to be calculating VThev? Which conditions are you going to be calculating your RThev? This is the most important part, because each and every theorem that you're going to have, it has got its own steps. We can't be talking of VThev when dealing with superposition. We can't be talking of the Thevenin voltage when dealing with maybe Norton's theorem. We have to know what is required on each and every theorem that you are given in your syllabus. That is what I'm trying to explain. All right, so anyways, let us see here. I just want you to see the stages that you're going to take for the Thevenin. The first thing is to remove the load resistor, RL. We are going to be working with the load resistor. So you have to remove that load resistor, RL, or the component contained. So the moment you remove this RL, what you're going to do is to find or to determine the Thevenin's. All right, the Thevenin's resistance, this one is another step that you're going to do after you've shorted the voltage sources, which is fine. But what is important, or what is best, is for you to remove your load resistor. Then from there, you find your Thevenin's voltage, because it is calculated from that circuit direct or VS by usual circuit analysis method. All right. Then after that, you remove the voltage sources that you are given, or you short the voltage sources that you are given, replacing with the internal resistance if there is a resistor. Then you find your RThev. So following that way, it's going to be easier. All right, then you replace this on the equivalent circuit, the voltage that you've calculated and everything. You are going to have this on the what is referred to as the equivalent circuit of what? Of Thevenin. So we are going to use the equivalent circuit to determine now the current across what? Across the load. So this is circuit. All right, let's just save this so that we can find the current across the load. And also sometimes you can be given a condition whereby the load resistor is in series with other resistors. When given this in series, you have to remove all the resistors that are together with your load resistor because they carry the same current. I explained that in another video. I think it was our last video that I talked about this condition of RL being connected in series, and you have to remove that. As the moment that you remove that, remove also with those resistors that are in series because they'll be at the same point. So in effect, in the same line, so they'll be carrying what? The same current because they are in what? In series. All right, let us check another part, which is on 1.2. 1.2, we are now given explain the following Kirchhoff's laws. All right. Okay, so sorry for that. The delay, something that is happening. Okay, so I asked you to explain the following Kirchhoff's laws in this case. All right, we've got the first one, which is the first law. So the first law, we are talking about what? We are talking about the current law in this case, whereby we are simply referring the sum of current towards a junction is equal to the sum of currents away from the junction, or the algebraic sum of these currents at a junction must be equal to what? Must be equal to 0 in this case. So that is let us just have this in a simplified part so that we can understand this. So this is the sum of the currents flowing into that junction is equal to the sum of currents flowing out of the junction. So you'll be working with the junction like I was explaining from this part. So that is the condition that you're going to have when dealing with the first law, or you can talk about the algebraic sum of currents must be equal to 0, right? Then the second law, which is our voltage law, which is referring to a closed loop. It must be from a closed loop, and if you work the algebraic sum of the voltages, they must be equal to the total voltage, or the voltages in a closed loop must be equal to 0. That's what we are simply saying. So this is what we are given here, that in any closed network, the total voltage around the loop is equal to the sum of all the voltage drop within the same phase, which is also equal to 0 if you talk the sum of all the voltages. But if you talk about the voltage drops, we're going to have the first voltage drop and another second voltage drop, which is equal to the sum, which is actually equivalent to VT, which is the total voltage in that circuit, depending with the loop that you are taking. And these voltage drops are simply current times resistance. Maybe it's current times resistance, maybe it's current 1, this is current, depending with what you're given, but it's simply current times resistance that you're going to work with as the voltage drop. So the moment I take these to this side, it means the total voltage now is equal to 0. That is, the algebraic sum is now equal to 0. But on this case, it was from the algebraic sum of these voltage drops should be equal to the total voltage in that loop that you are working with. That is where you end up with the 0 that we're talking about. So there you can explain in any way that you understand one and the same thing. All right. So 10 marks for that. Question number 2 that was we are given in this case. Let us check a voltage of 200 and okay, we are given the angle there of 30 degrees. That is what we have in this case. Let us see how we are supposed to attempt this one. Sorry for that. So here we are given a voltage source of 230 degrees is applied to 2 branches connected in parallel. So we've got 2 branches in this case, and if we are to consider the 2 branches are of 60 degrees and we've got 40 angle of minus 30 degrees amps, which is the current. Calculate the impedance of each branch and the total impedance of the circuit. Take note, we've got 2 things to consider: the total impedance and actually the impedance of each circuit, and also the total impedance in this case. All right, so we're given a condition whereby we have got 2 branches that are being connected in parallel. So I'm just gonna take these 2 represent our impedance in this case. All right, so we've got something of this nature, just a sketch of what is happening here. This is something of this nature. All right, so we have got the first part of our impedance. So this part is actually carrying, we do not know, is it going to be a resistor and an inductor, a resistor and a capacitor? We do not know. So it's just going to take it as the impedance. We do not know exactly. So maybe this is your second current, this is your first current, depending with how you want to present your information. You can just say this is my first impedance, this is my second impedance, meaning to say I'm talking about current, current 2, and also the total current. So if these two are in parallel, what is it that you're supposed to consider? It is the voltage that we are going to have here. The voltage that we are going to have is the same. We are going to have the same voltage throughout the impedances that we are talking about. So each impedance that we are given here is going to be affected by what? By the voltage. But here we are given the currents. Take note here, these are the currents that we are given from the voltage of 200 volts. Okay, so let us just take our information, the voltage 200 volts here. So we've got the supply volt of 200 at an angle of 30 degrees. That is our supply voltage, and the other currents, which is 20, angle of 30, 40, angle of minus 30. All right, so these ones you can just indicate the way that you want. You can just have this, it was 20, angle of 60, and the other one is 40, angle of minus 30. So you can just indicate the way that you want. These are currents that you're given. So these are currents, the current flowing here, the current flowing here. So the question is for us to calculate the impedance of each. We need to say we need Z1 and Z2, or you can write in terms of A and B, ZA, ZB. It's up to you. But what is important, like I was saying, is that the voltage is the same throughout. So in order for us to have impedance, we know that impedance is the voltage over the current. So meaning to say the impedance across this first part, which is Z1, is going to be V total over the current in that branch, which is I1, because we have the current. So we can calculate our impedance. All right, so that's our impedance. You can substitute your values, V, which is 200, angle of minus 30 degrees, divided to the current one, the current flowing. All right, this is a positive here, the voltage here, this is a positive 30. All right, then the current one here, which is a negative, right? So this is a 40, angle of what? Of minus 30 degrees. So we are dealing with a voltage and current in this case. And remember, from your simplification of complex numbers, if you're dealing with the polar form, you are going to divide these two. All right, then for the angles, you are going to subtract. So for the angles, you subtract. I explained this. That's R1, theta 1 over R2, theta 2. We are simply going to divide R1 over R2. Then for the angles, you subtract theta 1 minus theta 2. So we are going to divide these together. Then for this part, you are going to subtract for the angles. So do not confuse to say you are going to divide the angles. All right, so that will be 5. And if we subtract 30 minus 30, take note there's a negative. So it's 30 minus 30 like this, which is going to give you 60 degrees from your calculator. That is our Z1 in this case, which is the impedance. And this impedance is given in what? In polar form. And as we can see, we are asked to calculate Z1, which is the two impedances, this part, and also the total impedance. You are going to see that in order for you to calculate the total impedance, considering the concept of being in parallel of the product over sum, you are going to be working with the sum of these impedances. So it is also best that you just give also that what is the equivalent of this in rectangular form. So you can just write in rectangular form. All right, so this is in polar form, or we can have this in rectangular form. So in rectangular form, this is what you're gonna do, just convert direct on your calculator. I talked about this part of conversion using our calculators. Let us just see for revision sake. All right, so you're gonna have, we want to change to rectangular form. So this will be shift. I must have this shift rectangular form, which is a negative there. Then we have our value. Just press these values as they are, 5 followed by 60. So it's 5. Then separate this 5 with 60 degrees. That will be a shift. Use this comma. So that's a 60 degrees in this case. All right. So this must give us the value in rectangular form. Remember, in rectangular form, they are saying this must be in the form of x plus or minus jy like this, whereby for the real and for the imaginary part. So that's why you see your values are given x and y. So the x is the real part, which is 2,5 in this case. All right. So meaning to say our z can be given as 2,5. Then the value of y here is a positive. So that means we're going to have plus j, the value of y, which is 4,330. So that's 4,33. So we are going to have 4,33. So that means we are talking about Z1, which is this part of our impedance, or this part where we've got our Z1. We are talking about having a resistor and an inductor. Remember, the inductor is the one that adds from Z is equal to R plus J XL. We know that this is an inductor, whereby here we are given XL. So this represents our XL, and it means here we are talking about having a resistor and an inductor. It's an RL second. We cannot see that from the current. We can see that from what? From the impedance, because the impedance gives us the format of what? The format of an inductor or a capacitor. If it is a negative like this, it means it's a capacitor. So that is why we can check this now from what? From the impedance, not from the current that you are given. So that is how we can check to say, okay, this is an inductor and a resistor, or we've got a resistor and an inductor. We do the same thing just like what we applied here, but now on Z2, because we calculated for Z1. So for Z2, the impedance, this one, we are going to have the same thing, the voltage over the current, that is I2. So that means our Z2 is going to be the voltage, because I said the voltage in parallel is the same. So the voltage here is going to be 200 angle of 30 degrees over the current to here, which is 20 angle of 60 degrees. All right. Just like I said, in polar form, you are going to divide these two together, which means you're going to obtain 10. Then for the angles, you subtract in polar form. So that's 30 minus 60, which is minus 30 degrees. You subtract the angles, all right? So this is a simplification that you're going to have for our Z2, which is fine. You can just leave our answer like this. But because of later calculations that we need to make, we do not know what's going to happen with this. So we just have to convert also to rectangular form, so that we can use that value in simplification if there's a need for us to use something that is not in rectangular form. So it's the same conversion, just like the previous part. Let me just take you again through the calculator so we can check what is happening here. So this is what you're going to have this time. That is, we want to convert to rectangular form. So it's shift to rectangular form. So we've got a 10. Separate this by negative 30 as it is. Take the sign as it is. So that is the value of x, like I said, on the format, the value of x, which is 8,660 in this case. So we're going to have 8,66. Then we move on to the j part. The j part, which is the y value, the y is carrying a negative. So that means we've got negative j5 like this. So which means we are talking about an RC circuit, a resistor and a capacitor, whereby this is our XC. So that is going to be our Z2 in what? In rectangular form, just like that. But if you leave your answer at this, you've actually calculated your impedance. I'm just saying if it is a condition that you might need these values, but obviously if you are to use this formula that I'm explaining, that I'm going to explain for calculating ZT, you will need these values, unless if you use another way. So remember, it was not only Z1 and Z2, they also want us to calculate what? The total impedance of the circuit. So we need also the total impedance of our circuit. So for the total impedance, what are you going to do? We have got Z1 and Z2, which are in parallel. So you can just consider product over sum here, all right? Because these two are in parallel. So I'm just gonna use this, just gonna take advantage of this space here so that you understand me, guys. All right. Remember, we calculated our Z1 here. All right, we have got our Z1, which is 5 angle of 60 degrees, or we can just have it as 2,5 plus J 4,33 ohms. All right, just gonna remove this part for the meantime. Now, this is what I want us to understand from the Z1 that we calculated and the Z2 that we calculated. And we can see that these two, they are in parallel, Z1 and Z2. So it means to find ZT, we can use this concept, we can use product over sum. So we can obtain our ZT from the product over sum, that is the product of Z1 and Z2 over the sum of Z1 and Z2. All right, I explained about this typical questions whereby you're dealing with multiplication is best in polar form, addition is best in a rectangular form. If you are adding the complex numbers, add them in rectangular form. If you're multiplying or divide them in polar form. So we are supposed to find our ZT in this case, which is the product of Z1. Take note the impedances, which is our Z1 in polar form. We got 5 angle of 60 multiplied to Z2 in polar form, which is 10 angle of minus 30 degrees. So that's Z1 times Z2 over the sum of Z1 and Z2. So for the sum, you can write this as they are in polar form, then you convert, but already you converted to rectangular form. So for the sum, it's best for you to work in what? In rectangular form. So you're going to take Z1 in rectangular form, which is 2,5 plus J 4,33. All right. Then we are going to add this to our Z2. Remember our Z2, we got here 8,66. So this is 8,66 minus J5, like that. All right. So here we are adding, we're supposed to have a bracket. As you can see, plus is going to affect this. It becomes a plus, and this it's a minus. So the plus does not affect anything. All right. So that is how we best to simplify this part. If you're dealing with a combination of product and sum, know what to use, know what to apply for multiplication, know what to apply for addition. So it's going to be easy for us to multiply here because we're in polar form. So you simply multiply the numbers together. Then for the angles, we add. So that's 5 times 10, which is 50. And the angles, we're going to add 60 plus minus 30. So if we add 60 plus minus 30, that will be at 30 degrees in this case. All right. So this will be 30 degrees. We do the same concept for rectangular. We're going to add what corresponds to rectangular, to the real part, 2,5 and 8,6, the real part. We are back to our complex numbers, mathematics and 4. So we are going to add 2,5 and 8,66. So if we add this, we are going to obtain 11,16. Then the J part, you combine it separately also. So that is going to be 4,33 minus 5, which is going to give us negative 0,67. So it's negative J 0,67. So that is the resultant that we are having in rectangular form after combining these that are in rectangular form. But as you can see, we want to calculate ZT, and this is in polar form, this is in rectangular form. We are talking about division, and I say division and multiplication, it's best for us to deal with these in what? In polar form. So we are supposed to convert the denominator, this one, to polar form. It's best for you to work with the division in polar form. So our ZT is going to be 50 angle of 30 degrees. We convert this to polar form. So we're going to convert this to polar form. So just like our conversion to rectangular form, we're going to do the same thing, and we are supposed to expect our answer to be in the form of r theta in what? In polar form. So that's on our calculator. We can just convert this direct. We are going to have so this time we are into polar form, so it must be shift polar form. All right, we are going to polar form. Remember, we are going to polar form, so it's going to be shift. We go to this polar form, which is the plus. All right, so we have got 11,16. That's 11,16. Then the other part of the imaginary, it's separated. We separate the imaginary from the real. So this is minus 0,67. So you're going to separate, shift this comma, minus 0,67, 0,67, like this. All right, so it's gonna give us the value corresponding in polar form. Like I said, in polar form, you're going to expect to have r angle of theta, whereby we are given the resultant and the modulus, all right, and the argument, or you can just say the magnitude or the modulus or the resultant in this case, and this is our argument, the angle, which is your argument in this case, all right. So that is what you're given here, r, which is 11,1800, so it's going to be 18. So we are going to have 11,18. All right, so let us just have this 11,18 at an angle of what, which is our theta in this case. So theta is this one. You can just move this side. You've got your theta. Our theta is negative 3,4356, which is going to be negative 3,436. All right, so that's negative 3,436. So that is what you're going to have in this case. All right, we have our answer from what we had before in rectangular form. We have converted it to polar form, just for the simplification purpose, to say, because we are dealing with a division, and when you are dealing with division in complex numbers, you have to divide them in what? In polar form. Addition in rectangular form. Subtraction rectangular form. Multiplication polar form. That is what you just need to understand, so that when you are at this stage, it will be easier for you to simplify, because here you are simply going to divide the numbers together and the angles you subtract. All right, so if we divide these numbers together, what are you going to obtain? 50 divided by 11,18, we are going to obtain 4,472. All right, then we move on to the angle. We are going to subtract 30 minus 3,436. If we subtract, it's 30 minus minus. All right, so it's going to be 30 minus minus, which is going to be 33,436 degrees. So this will be 30 like this, minus, and there's a negative, minus 3,436 like this. So it will be minus minus, which gives us a plus at the end. Or just use your calculator, guys. That's why you've got calculators in exam. So like I said, this was another way of simplifying this question, dealing with the total impedance from Z1 and Z2, because we are told that these two, they are in parallel. So you can use product over sum. All right, what if I do not want to apply this Z1 and Z2, and I want to be working from the currents? All right, this is another way that I can do and find the same answer that we are having, or the same impedance that we want, which is ZT. All right, this is what I want you to understand, guys. Remember, from our circuit here, we want to analyze our circuit. We have got the total voltage of our circuit. And from the currents that we are given, I1 and I2, in parallel, we know that the total current is equal to the phasor sum of these two currents. So meaning to say, we are referring our total current being the current I1 and the current I2, which is the phasor sum from what we are given. If we are able to calculate the total current, it means we are able to calculate the total impedance, because we understand that the total impedance is going to be the total voltage over the total current. And we have got our total voltage here. And what is just left? Total current, and the formula we have. So meaning to say we can also use this formula to calculate our total impedance. All right, so that is another way that we could have calculated our total impedance. So let's start by calculating the total current first. So we are going to have our total current from I1 plus I2, but now it's addition, and I said addition, it must be in rectangular form, but check now, these are in polar form. All right, let's just try to convert them after writing. So that's I1, which is 40 angle of minus 30 degrees plus I2 in this case, which is 20 angle of 60 degrees. So this is the phasor sum of our current in this case, all right, which is going to be 40 angle of minus 30. If you convert this to rectangular form following those stages that I was showing you guys, you're going to obtain 34,641 minus J20. So it will be minus J20 in this case. You do the same thing for 20 angle of 60. All right, let me just, but we are simply applying these guys. All right, so just gonna have something of this nature here. I just hope you are now understanding this part of our conversion part. All right, so we want to convert to polar to rectangular form, so it's gonna be shift rectangular form 20 separated by what? By 60. So that's shift comma 60 in this case. All right, so you get the value of x and the value of y, which is the value of x, that's 10. So that will be plus 10. Then y there is a positive, which is j 17,321. So it's going to be plus j 17,321, like that. So this we have converted to rectangular form so that it's easier for us to combine this. We cannot add direct, which is fine, like to simplify separately in what, in rectangular form for simplification purposes, because we cannot just combine that direct. All right, so we are going to obtain our total current from there, which is adding the real terms together. So if we add our real terms together, 34,6 and 10, that will be 44 in this case, 721. Then we combine the imaginary part, that's minus J10 in this case, and J17,321. So we are going to combine this negative 20, so negative 20 there, plus 17, which is going to be a negative 2. It's going to be a negative 2,679, which is negative J 2,679. So this is our current in amps, and this current is in rectangular form. But as you can see, we are going to need the current to be divided. We are going to need to divide by the current. The moment we talk about division, it means we must have this in polar form. Like I said, division is best in polar form. So we are forced to calculate or to change this, our total current, to be written in polar form. This is our rectangular form. So let's convert to polar form, just direct on our calculator again. We're gonna convert this. That is to polar form, shift polar form. Oh, sorry, that is, we are going to polar form. So it's shift polar form here. We have got 44,721. All right, then we separate this, which is shift comma here, negative 2,67. It's negative 2,679, negative 2,679, like that. All right, so you can close your bracket equal to, so for the value of R, remember in polar form, we've got R angle of theta. So that's the format that you'll be given. So that is our R here, 44,801. So that is right. Am I missing any value here? Am I missing any of the values here? All right. I just want to check something. If I am missing any of the values, negative 2,67, I'm just, my values, the one that I calculated before and the one that I got here is different. All right, 44,8. All right, this is 44.721. And this is, all right, I'm just going to, just let me redo this, guys. I want to confirm with what I got in the first place. Remember, All right, this is 44.641. This one, 6 here, because you're adding a 10. So this is a 641. I'm surprised to say, why is this now giving me another value in this case here? All right, this I mixed up on my writing up here. This one and this one, guys. If we add this one and this one, it's a 44. So that is a 44,641. Okay. Then, okay, this part and this part, which is fine. Okay, so I was wondering what is happening with my answers here. So that is 44,641, 641. Then we're going to separate this with the negative 2 comma, that's negative 2,679. All right, like this. So it was gonna, all right, I need to close this one. So it's going to give us 44,721, which is exactly what I'm expecting here. All right, so this is the value of R, which is 44,721. So you're going to have 44,721. Then the angle, remember we are in polar form, so we've got our theta there, which is going to give us a negative. That's negative 3,434 in this case. So this will be a 4, right? So this is what we are going to have as our total current in amps. And take note of your calculations. Please be very, very careful on your calculations. This is your total current. Why calculating the total current? Because we need this current in order for us to have the total impedance. Like I said, the total impedance is voltage over the total current. So that means our total impedance is going to be voltage over the total current in this case, which is, like I said, it's best in polar form. We've got our voltage already in polar form, 200 angle of 30 degrees. So this will be 200 angle of 30 degrees to the current, our total current, which is 44,721 angle of minus 3,434 degrees, like this. All right. So that is going to give us the total impedance, and this impedance being in what? In ohms. So the nicer part of having this in polar form is that we can simply divide this part, all right, the resultant or the magnitude. Then for the argument, you subtract on this on the angles, all right. So let us just divide and see what you're going to have. We must obtain the same answers just like the previous part where we used the impedance is direct. So this is 200 divided by 44,721, which will be 4,472. So you're gonna have 4, all right, sorry for that, 4,472. And the angles, we are going to subtract 30 minus, so that will be a plus there, which is 33,434 degrees. All right, so that's our total impedance. And since we have to calculate the total impedance and we have it, there is no need for us to convert this to rectangular form, because we have what we need, guys. We are not going to use this to calculate anything. So if we check the first answer that we calculated from, the impedance is the product of Z1 and Z2 over the sum of Z1 and Z2, because those impedances were in parallel. We obtained the total impedance as 4,472, 33,436. Here it's 434, just that difference of 2 here, but it's one and the same thing. So you're going to choose which method to apply. Are you going to work from the impedances? Are you going to work from the current and the voltage? Still, you are supposed to obtain the same thing. All right, so these are the two stages that or 2 steps that we could have taken, methods or ways that we could have taken to calculate our ZT, total impedance, from that circuit that you're given. All right, 2.2, we are now given an LC circuit resonating at, all right, so we're given the resonant frequency there. So it is resonating at a frequency of 6 megahertz. So we've got the resonant frequency, which is at 6 megahertz, and I've got the Q factor of 300. All right, find the total bandwidth in this case. So remember, the total bandwidth is the change in F or which is our bandwidth in this case. All right. So, and the edge frequencies FH and FL. All right. So we can calculate first our bandwidth in this case, then we can calculate our FH. Remember, FH is simply from the resonant frequency and the bandwidth. So it's going to be the resonant frequency plus we are going to add. Then for FL, which is the lower part, you subtract. All right. So this is going to be FR plus the bandwidth over 2 in this case. Okay. If you're talking about FL, it's going to be a minus FR minus the bandwidth over 2. So as you can see, between these two, we need bandwidth. We are going to need the bandwidth in this case between these two. So where are we going to have it from? From the resonant frequency and the quality factor. It follows also that the bandwidth is equivalent to the resonant frequency over the Q factor in this case. All right. So we're just going to substitute FR, which is 6 mega 6. That's mega times 10 to the exponent of 6 over Q, which is 300. So this was going to give us 20,000. So we are going to obtain 20,000 hertz. This is frequency, which is same as 20 kilohertz. You can just write as 20 kilohertz in this case, right? So that was what we were supposed to have. And after that, we can use this 20,000 hertz or 20 kilohertz now to calculate our side or our edge frequencies in this case, which is FH and FL. All right, so from FH, you can just substitute here, which is FR, our resonant frequency at 6 megahertz. All right, plus our bandwidth over 2. So you're going to have 20,000 over 2. So that's it. You're going to have 20,000. All right, that's 20,000 over 2. All right, like that. So that is going to give us something like 601 0000 like that, which is that's 3. So you're gonna change that to mega. It can be converted to megahertz. This one, right? So that will be 6,01 megahertz. And for FL, we're just gonna substitute here. We're just gonna have a negative. That's the only part that you're gonna change. Just gonna have this as a negative 20,000 over 2 like this, which is going to give us a 599,000 like that. All right, that's again, we can convert this to megahertz, which is going to be 5,99 megahertz. We divide by 1 million in this case, or by multiplying by 10 to the exponent of -6 to convert to megahertz. All right, so that was it. I think just direct 1 mark each there. All right, so these are some of the things that you just do not have to take much time in exam. All right, 2.2, an alternating voltage is an RMS value. So this time we are given the RMS value of 106,38 volts. Calculate the peak value. All right, so remember the RMS value is actually taken from the peak value, which is 0,737 times the maximum value or the peak value in this case. All right, then also we talk of the average value, which is equal to 0,607. This one, the 0.7, then this one is 637 V. All right. Also, we are given this from our formula sheet, and we are supposed to be careful on our formulas there. From our formula sheet, we are given that's 0.707. All right, let me just confirm. Yeah, that's 0.707 there. Then we can calculate everything here. Let's just see 2.31. We are asked to calculate the peak value, which is the maximum value. So the maximum value, which is Vm, we can just take from VRMS here, since we can see that VRMS is 0.31 or 0.707 of Vm. So you can just make Vm the subject. If we divide by 0, 707. So you're gonna have the RMS value over 0.707. All right, so that's our RMS value, the one that we are given here, which is going to be 106.38. All right, then we divide to 0.707. That's it. We are going to obtain the peak value, which is the maximum value. That was going to be 150.46671, which is going to be 467. All right, volts. And the other part is the peak to peak value. So the peak to peak, it's the one that we take in between maximum and maximum, or the peak value and another peak value from negative. All right. So that is going to be simply twice of what? Twice of the maximum value. All right. So that is our peak to peak value is simply twice or 2 times the maximum value or the peak value. All right. So you're going to have 2 times the maximum value of 150.467. So that was going to give us 300. So you're going to obtain 300.934 volts. So that is what you're supposed to obtain on the peak to peak value. Then the other part was to calculate the average value. So the average value, since we now have VM, which is the maximum value, you can calculate our average value from the formula. Remember, this formula we are given in our formula sheet. All right, so that will be the average value is given as 0.637 times the maximum value. So this one is just a substitution, 0.637 times our maximum value, which is given at 150.467. So that is going to give us the average value of 95.84747, like that, which is 847 volts. So that is the idea there. All right, how many marks for that? 3 marks, just 1, 1, 1, 1. Okay, this was just 1, 1, 1, 1. Yes, okay. Name one property of a resonant circuit. All right, if the circuit is at resonant, we can talk about the condition of XL being equal to XC, the impedance being equal to the resistance, and so forth. So let me just show you just a little of this part that I'm having so that you can use it in addition to your revision. So for the inductance, reactance is equal to the capacitive. So we've got inductance, reactance is equal to the capacitive reactance, which is XL being equal to XC. And also the impedance is equal to the resistance, Z is equal to R. Then current is going to be maximum if you're talking about a series resonance. For a parallel resonance, our current is going to be taken as a minimum in this case, right? So I think we're able to get one there. It was just one. Okay, name one property. So you just need one part from what you have selected there. So this is how we can answer that type of a question. Then we are given on question number 3, a 5-volt stabilized power supply. So talk about a power supply in this case to be produced from a 12-volt DC power supply input source. The maximum power rating PZ of a Zener diode. So this one, it uses a Zener diode. Use the Zener regulator circuit above and calculate the following. All right, so this is the application of a Zener diode. In this case, a Zener regulator. So remember, from our Zener regulator, I'm just gonna have a sketch in this case. Remember our Zener regulator, we've got the series resistor RS, and here we're gonna have our Zener diode. All right, and we're gonna have the resistor that is connected to the load, in this case at the output, which is our load resistor. Yeah, something of that. So this will be from a full wave or half wave rectifier there. Then we've got our VIN, which is the unregulated voltage in this case. All right, then that is RS and IS. Then our Zener, which is our Zener diode in this case. According to the currents, the supply is the one that is going to give us this current of IS. which is going to branch into the Zener, and the other one is going to branch into the at the load, which is the load current. At the output here, we've got our load current, or we are talking about V out, which is simply VL at the load. Okay, so that is just the basic of what you're given there. So the question was, we are given that is a 5-volt stabilized power supply is required to be produced, which is the output to be produced from a 12-volt DC supply input. So you're given the input of 12 volt and the output of 5 volts in this case. All right, so we've got an input Vin, which is 12 volts here at the input, and at the output we are given 5 volts, which is V out in this case of 5 volts, and also the power across the Zener diode of 2 watts in this case. This is the maximum power. According to this information, they are saying the maximum power rating PZ. All right, use the Zener regulator circuit above to and calculate the following: the maximum current flowing through the Zener. So you're asked to calculate the maximum current across the Zener. All right. So in order for us to obtain or to calculate the maximum current across the Zener, what is it that we're gonna do? It follows that the maximum current across the Zener from the power that we are given is going to be the power over the Zener voltage. All right, so it's gonna be power over the Zener voltage. So what represents the Zener voltage? That will be the case, because here we are not told about this voltage. This is the voltage at the output. So the Zener voltage is the voltage that you're going to take, which is at the output. So you're going to have our power in this case, which is 2, over the voltage at the output, which is 5. So this was going to give us 0.4 amps. Remember, we are talking about the maximum current, which is measured in what? Which is measured in amps. So our maximum current is going to be 0.4 amps. All right. Then the other part that we are given, and you can even write it in milliamps, which if you want, which is going to be times 1,000. If you multiply by 1,000, it will be 400 milliamps. That one is up to you if you want to write it that way. But that is the maximum current. Then the minimum value of the series resistor RS. So the series resistor is going to be taken from the voltage in. So far we have the voltage in and the output voltage, which is the voltage across the Zener, and the resistor and the current across this part here, which is the current across the what? The current across the series, because we do not have the load resistor. It's not considered in this case. We are not having the load resistor. So we're going to interchange or to formulate your formula in a way of what you are given. So you're going to have this RS from voltage over current. So our RS is going to be V in minus V out in this case, which is the voltage across the Zener, because we do not have VL at the end. I mean, we do not have a resistor to be considered there. So we are going to take it from this Zener. So we're going to take that across the Zener. So we're going to use VZ over IS in this case, which is Imax, which is the current that is flowing across the Zener. We're taking it in this way. It's no longer going this direction. We are taking it, all the current taken in this circuit, that will be at maximum conditions. All right. So that is our Vin of 12 volts minus VZ, which is the voltage there of V out, which is 5, over the current, which is 0.4. So that is how we can find our RS in this case, and that will be 17.5. So you're gonna have 17.5 ohms. And the other part there was to calculate the the load resistor RL now. All right, the load current. If the load now, as you can see, we are given the load this time. All right, so you can consider the load. This time we have the load. So they are saying we are supposed to calculate IL if we have got a load of 1 kilo ohm connected across the Zener diode, which means we are simply going to use the output over the input, VL over RL in this case. All right, so that is 3.13. So the current from voltage over current is going to be the voltage at the output over the resistance at the output in this case, all right, which is RL. The voltage at the output, which is 5 in this case, so that is going to be 5 over RL, because we are given here, guys, the resistance at the load of 1 kilo ohm. So it's going to be 1 kilo ohm. That's 1 times 10 to the exponent of 3, which is going to give us 0.005 amps, right? Or you can just write this as 5 milliamps. If you multiply by 1,000, you get 5 there. And the other part was to calculate the Zener current at full load. So at full load, that's where now we can consider the currents flowing into the circuit. IS is equal to IZ, the current across the Zener, plus the current across the load. As we can see from our Kirchhoff's current law, we can use that to calculate the current across the Zener in this case. All right, since we are saying from our Kirchhoff's law, all right, it follows that IS, which is the current entering, is supposed to be equal to the sum of these two currents, the current across the Zener and the current across the load. So we are going to have this as the current across the Zener plus the current across the load. So since we want the current across the Zener, we can transpose the one across the load to the other side so that it will be a negative. That's IS minus IL is equal to IZ. That's the current of the Zener at full load in this case, all right? So meaning to say, we are going to use IS, which is our IS, remember, is the one that we had previously from the Zener calculations. Before we had RL. What was our current? Our current was 0.4 before having the load resistor. The load resistor is the one that made us to find this IL. We are not having that, so we're going to consider now when the load resistor is there, the load current is 0.05. So you're going to subtract your load current of 0.05. So that is how we can end up with this part of calculating our IZ from this formula. Okay, so let us substitute our values. 0.4 minus 0.005, which is going to be 0.395 amps. All right, remember this is the current, so that's the current across the Zener. Let me just save this properly. The current across the Zener in this case. Okay. So that was 8 marks, 4 times to each 2 marks, 2 marks. Neatly draw and label the symbol and characteristic curve of a PN junction. All right, we're talking about a PN diode in this case. All right, so we need from the diode to the characteristic curve of that PN diode. All right, so remember, that's the circuit sim that we have on a diode, whereby we have got the anode and cathode, and also the construction part, depending, is it PNP or an NPN? I mean, is it PN or NP, like on the direction, right? So here we are talking of a PN, meaning to say our anode positive, our cathode being negative. So that is the cross section that you're going to have for a PN junction in this case, all right? So the question is, we are not just supposed to have these symbols, we are supposed to have also the characteristic curve. So that is what you're going to have on your characteristic curve in the forward bias and also the reverse bias. Do not confuse or to interchange this with a Zener diode. For a Zener diode, you're going to have something different, just a little bit of similarities, but everything will be different there. All right, so that was our Zener, I mean, that was our diode, our PN, given a PN in this case. Then 4.1, we are given choose a waveform from the column B that matches the representation of in column A. So we've got column A, write only the letter A to E next to the question number in this case. All right, so this is what we have, and just gonna see. So the column A, it's just we are having an output which is that's a straight line. It is a straight line. It means it's just a regulated wave. In this case, this is now regulated, right? Before it will be like this, okay? Before, so this is now a regulated now wave. So that is, we are choosing from B. So instead of writing regulated wave, we're just going to write C. Okay. Then this one, as you can see, it is still having some ripples that are there. So it's from a filtered form. All right. So it's a filtered waveform, this one. All right. So that's E. And we've got this form whereby it's affecting only on top, like the output is just on top. All right. The like positive. We do not have anything that is affecting the negative. It means it's now being rectified. It's from a rectifier, which can be now be smoothened. Remember, from a rectifier, that's where we're gonna be joining like this. All right, so that it's now a rectified wave when it is now a straight line. So this one is simply a rectified waveform in this case, right? Because it's a waveform, this one, right? So you're gonna consider B as the best answer there. Then 4.14, this one, it's the input actually, like we're talking about a sinusoidal function in this case. So that's a step down waveform in this case, all right? Exactly. So that one, it can't be, was non-sinusoidal, it means it's not sinusoidal. So you can't use this one. So okay, so you're supposed to be careful on our answer. This one is a sinusoidal function, a sine wave that we are seeing. So you can just put it as a step down waveform. All right, so list two types of instrument transformers. The instrument transformers can be taken from current transformers. All right, yes, we can talk of current transformers there. We can also talk of the potential of voltage transformer. So you can talk of the voltage transformer also. Voltage transformer, which is a potential of voltage, all right? Then list any three differences between a bridge and a center tapped circuits. All right, so this one, let me just show you this one. There are a lot of differences that we can take note into consideration for a bridge and a center tapped. So a center tapped and a bridge, these are two different things that we are talking about, guys. All right. So in a bridge, two diodes always conduct. Remember, a bridge, you're having four diodes. So two diodes, they always conduct simultaneously, meaning say two diodes and another two diodes there to make them four. So do not be confused. There is simultaneously there to say that at the same time. So the two diodes and the other two diodes all together, there will be four, resulting in the forward voltage drop double that of the center tapped circuit. And also in a bridge circuit, the PIV, that is current voltage across the reverse bias diode, is equal to the maximum voltage, where the PIV of the center tapped circuit diode is twice the maximum voltage. All right. Then we talk about a bridge circuit uses four diodes in contrast to the two diodes of the center tapped circuit. All right, so this was supposed to be the first statement for us to note, okay, which is fine. Then a bridge circuit performs a full wave function without the use of center tapped transformer. Then also a bridge circuit has the advantage that it can also be directly supplied from the AC source without the use of a transformer. So these are some of the things that you can consider over or between a bridge and a center tapped circuits, in this case from our rectification part. We talk about these bridge and center tapped and so forth. All right, so we've got question 5. Mention any three characteristic curve of a transistor. They are saying we must mention three characteristic curve of a transistor. So there we can have the input curve. All right, so let's just have for the characteristic curve, we can have the input characteristics. I want you to take note. If you checked, I talked about calculating of gain, those gains and so forth from in fact the application of our H parameters and so forth, whereby we talk about the input curve, characteristic curve, and output, and also the transfer characteristic, whereby you need to know the condition of the circuit that you are working with. Is it a common base, or is it a common emit? We talked about that. So this is what we are seeing in this case here. The input characteristic curve, whether in terms of current, which will be IB, and in terms of voltage, which will be VBE, output characteristic curve showing IC and VCE, and the transfer characteristic curve showing IC and IB, which is some of the information that you need to know. On your simplification, you are supposed to understand this curve. So this is like what we are given here. We are asked to study Big 2 below and answer the questions that follow. So if we are to study here, we are given the input, which is the current IB in microamps. So this is the input current, which is our IB in this case in microamps. Then we've got this side, which is IC at the output, which is in milliamps. In this case, this current is in milliamps. So if you take here at the output, it corresponds, the first value here, it corresponds at 4. At the middle point here, it's 8. And the maximum value is 12 milliamps, which is taken, or which also must correspond to the input that we are given of the sine wave, which meaning to say, for us to be having a 12 at the maximum, our input here is supposed to be at 6. For us to have 8 at the middle, our input must be at 8. For us to have a 4, our input must be at 2, corresponding with also this side here that we are having 3 to 4, 6 to 8, 9, and so on. So that is the condition. I mean the 3 here to the line. Where am I reaching? This 3 to this point here, this value to here, this value to here. It can be like that. So here we are considering input and output. So take note of your values that you're going to consider: the minimum, this one at the mid, and this one at the mid, the maximum 6 at the input, the maximum 12 at the output. That's why they are saying study this. Do not just answer the question without understanding the diagram, because it's as you are asked to study. So analyze your diagram and understand what are you given from that, so that you'll be able to answer the questions. Like here, they are saying, which class of amplification is indicated by the above characteristic curve? All right. So they are saying, which class of amplification is indicated by the above characteristic curve? Give a reason for your answer in terms of amplification. If we are to take note, because we've got this part in the middle that gives us a maximum undistorted output here, so that can be class A. All right, it's because of all this taken to the mid. So this is actually a class A, all right? So let me put it this way. I think it can help us here. I think I have got something for you guys. So this is a class A. So that's a class A amplification. When the transistor amplifiers operate, point Q is in the middle to give a maximum and distorted output. All right, so that's there. We are referring to a class A amplification. And they are saying, give one advantage of the class amplifier named in question 5.1. So they are saying for the class A, what are the advantages of class A amplifiers? So it's because they've got low efficiency in terms of operating. These ones, they have got low efficiency in this case. All right, then determine the static current gain in this case. All right, so we've got the static current. Remember I talked about the dynamic gains and in fact dynamic values when we are dealing with all right, sorry for that. I do not want to remove this. I don't know what happened here. We talked about the issue of dynamic, and I was actually talking about common emitter and the common base amplifiers. Actually. All right. where I said you just have to consider the characteristic curve that you're given at the input and at the output. So there, the first part is to calculate the gain, which is the static current gain. So the static current gain is taken, these are the ones that you take at midpoints from the output. Gain, guys, is output over input, right? So for the static gain, we are going to have this from the output over the input. All right, that's 5.23. So we are gonna talk about the static current gain. That's current gain. So we're not talking about voltage. Remember, we have got the voltage here, but we need current only. So we're gonna take the current at the output over input. This is our input. This is our output here. So current at the output over the current at the input in this case. So the current at the output in this case, which is, okay, sorry, I'm still on that PDF. All right, sorry guys, I'm writing on another page while I left to share the screen. Sorry for that. So I'm saying the static current gain is simply the current out over the current in. So do not be confused on this part to say here this is voltage. Right. So this is, you are considering the input current, but like I said, according to these corresponding values, they are corresponding to 3, to 2, 4, and 6. But you have to take at middle values for static, right? So at the output, the one at the middle that you're gonna use here is 8 milliamps, which is times 10 to the exponent of -3, which is corresponding to what? To 4 microamps. Remember, at the input, our current corresponding is 4, measured in microamps. So we've got 8 milliamps at the output. That's 8 times 10 to the exponent of -3. At the input, at the midpoint, we've got 4 microamps. So that is going to be 4 times 10 to the exponent of -6. All right. So that is going to give us 2000 if you simplify properly. All right, that was our 5.23. Then 5.24 again is on the gain, but this one is a dynamic gain. The moment we talk about dynamic gain is now the change in current over the change in current at the out over the change in current at the input. That's for dynamic. So we're gonna have dynamic current gain. I'm just gonna write this in short, guys. So we're gonna have the change in current at the output over change in current at the input in this case. So at the output, the current changed in this case from a minimum 4 to a maximum, which is 12. So you need the difference between these 2 points. It's 12 minus 4 in milliamps, right? So that's 12 minus 4 in milliamps at the output. So we've got 12 minus 4 times 10 to the exponent of -3, that is in milliamps. At the input, from our current at the input here, we said the 4 corresponds to 2 and the 12 corresponds to 6. So we're going to have the difference between these 2.6 and 2. So it's going to be 6 minus 2 in microamps. All right, so that's 6 minus 2 measured in microamps. So 6 minus 2 in microamps, that's times 10 to the exponent of what? -6. So we're going to have the same answer here. Okay, we're going to have the same answer, which is 2000. So that will be 2000 also, just like the previous part, we obtained 2000. So this one was giving us the same answer. All right, 12 marks for that. All right, it was actually fine, this transistor. It was actually fine, 12 marks. All right, let's just hope we revise our theory, guys. Let's find time to revise your theory as much as you can. All right, then the other part we are given, indicate whether the following statements are true or false. Choose the correct answer and write true or false next to the question. All right, so let's check the first one, 6.11, which is an ideal op amp we have 0 input impedance. An ideal op amp, this is actually false. For an ideal op amp, it has got infinite input impedance. So this is false. The input impedance is actually infinite. All right. Then 6 is highly infinite. Okay. 6.12 in an ideal op amp, the output swings instantly to the amplified voltage value. It swings instantly, which is through to the amplifier. This is very true. This is very correct. 6.13, the main advantage of op amps is that they come in bigger sizes. No, it's impossible. These ones, they come in smaller sizes. All right, op amps, they are found in smaller sizes. So this is actually false. They are in smaller sizes. All right. Then 6.14, the gain of an op amp produces, all right, the gain that an op amp produces will be independent of frequency. Independent meaning say does not depend on the frequency, which is true. The gain does not depend on the frequency, so it is independent of the frequency, which is actually true. Independent, it does not depend. Remember our gain, the voltage gain from R1 plus RF over R1. There's nothing to do with frequency. There's just your resistances. There's nothing to do with frequency. So means it does not depend. 6.15, the ideal op amp can produce only a 0 voltage gain. This is very, very wrong. So this is false because for an ideal op amp in terms of the voltage gain, it will be actually infinity voltage gain. So it cannot be 0 voltage gain, it will be infinite. Then list specifications. The specifications applications of an operational amplifier are determined by connecting external components to the amplifier. List any 5 applications of an operational amplifier. So yes, not like the applications, the way like where are we going to have this in industry? The applications they are talking about, these are the types of amplifiers that the name of the amplifier tells us about the application of that amplifier. So these are just the amplifiers as the op amps as they are. You're just listing all the op amps that you have in your syllabus, which is we've got the inverting op amp, we have got the non-inverting, we've got the non-inverting op amp. If we even check, we also have the summing amplifier for the summation points. We also have the integrator. So these are actually things that are actually in existence that we are talking about. The differentiator. We've got the differentiator in this case. We also have the comparator. So in actual industry, if you talk about industry, these are things that are actually happening. And these are very, very mathematically programmed. These are op amps. They are mathematically programmed for any of its duties that is supposed to be operating in terms of this. Then question 7, we're asked to tabulate, that is just have differences that you're going to have between natural and forced commutation. In this case, we're just going to have this in form of a table between a natural and a forced commutation. So here I've got some of the things that you're given between the natural and the forced commutation. For natural, it requires AC voltage at input. Then forced, it requires a DC voltage at the input. No external components required. Then it requires external components. The AC voltage controller is used in controlled rectifier, whereby here it's used in chopper and inverters. Then we've got the SCR turns off because of negative supply voltage, whilst here the SCR, it turns off because of both current and what voltage. No power loss during commutation. Here there's power loss during combination on the forced commutation. Then we've got zero cost. Then we have got a significant cost to be applied. So that is the idea about natural and forced commutation. Then 7.2, we're asked to explain how an SCR is switched on, is switched from the on state to the off state. How are you going to switch it from the on to the off state? All right, so these are some of the points that you're going to take into consideration. You're going to reduce the current through it to less than the holding current. The moment you do that, you remove the anode current, then short circuit. So these are the steps that you're going to take. Reduce the current through it to less than the holding current, then you remove the anode current, and the last part is simply to short. So that is what we are given 2 marks for that. So any two there. 7.3 state 2 practical applications of an LA C SCR, which is LS in this case. All right. What are the practical applications? Where do we apply these? We can apply this in logic circuits. We can have this in actual logic circuits, and we can have this in our optocouplers. We can also have this in our optocouplers. It's the part that you can actually have 2 marks for that. All right, so I think it was fair enough. Like this theory that we are having here, it is like fair enough. Like the way it is given here, it is somewhat fair enough the way it is given. I don't know, but just see like. All right, then question number 8, studying Fig 5a above and answer the following question. What type of measurement is represented from 5a? This or 5a. So 5a, this one is for a linear measurement, this one, and this one is for angular measurement for 5b. So here we are talking about a linear measurement. So which can be used for linear measurement like linear displacement and so on. So if we check on the 5b, that one is an angular. Remember, these are potentiometer. This is a potentiometer, that one. So the B is for angular in this case, whereby you're dealing with maybe angular displacement in terms of your what? In terms of your measurement. All right, so that was the question here, where we are simply separating 5a and 5b. Then 8.12, they are saying make a neat labeled construction circuit showing a diaphragm to measure pressure. From 5a, from a linear measurement, we must have a diaphragm under a linear measure, meaning to say we must have a diaphragm under linear displacement. All right, so this is what I'm going to expect you to have for a diaphragm under linear displacement. That's what you're gonna have for the first part. All right, you're showing your bellows, the movement, the pressure. I think everything there is pretty clear for A, and also for B. In this case, I actually like. All right, let's just check the other part here. I want just to see something. Then for the B, it's actually one and the same thing in this case. All right, so for the B here, it's one and the same thing. We need the make a neat labeled construction and circuit to show the resistance elements if you apply, if the supply may be AC or DC connected to the measured displacement. Remember, the measured displacement that you're talking about is angular. So we are going to consider for what? For angular displacement, because the measurement there is angular for the B part. All right, for angular displacement, we are going to have it in this form. That is all the resistance element, the slider, and the mechanically coupled part in the shaft. I think you can just have these 4 marks for your construction and also the circuit. All right, so I think your diagrams, guys, just revise your diagrams as much as you know how to draw. Me, I'm not good at the drawing part, but I just hope you are good at that. As for me, the drawing part is not for me. My part is calculations. I'm good at calculations, and this. Okay, no problem. Draw a neat labeled block diagram. So you need of an elementary cathode ray oscilloscope consisting of the following components. So 10 marks for that. You must have each and every of the components from the cathode ray tube, the synchronization circuit, the time-based generator, the X amplifier that is in the horizontal, and the Y amplifier in the vertical. All right, so we're gonna have either of these 2 diagrams. Just gonna choose which one is best for you to draw. Like I said, me, I'm not good in the drawing part, so I just hope you'll be able to draw such and combine everything from the indication or showing of our cathode ray tube to the horizontal plane, which is having horizontal amplifier, which is the X amplifier, to the vertical amplifier, which is the Y amplifier in this case on the vertical position. Then we've got the volts per division, and also so you can also have it this way. I think this one is it's fine. Also, it's fine. It's just that you have to know your diagrams, guys. Like I said, I'm not going to explain much just for diagrams. This one, it needs you and your drawing techniques, not just to know your drawing, but just to at least know what is happening, like on each and every part. 9.2, we are given a calculation to be made from the oscilloscope concept. We are given or asked to study the figure above and determine the amplitude of the sine wave as well as the peak-to-peak value. Assume that the switch is set to 4,8. Take note, guys. The deviation that we're given is 4,8 volts per centimeter, and the probe at times 1. So here we are given at what 4,8 volts, which is in terms of the V per watt per dive, in this case per division that you are given. So the question is to calculate the maximum value, all right, which is in this case the peak value. That is our maximum value. So in order for us to know the peak value, we are going to take the voltage that we are given here. I mean the distance that we are given, because we are given per division, which is the deviation that we are given for the voltage. Remember, they are saying it's 4,8 volts per centimeter. So it's going to be 4,8 volt per centimeter, like this, like per 1 centimeter times. How many centimeters are we given to the maximum? It's 1,32. That is what we are simply saying here. So this cancels, we remain with the voltage. So that will give us the maximum voltage from there. So the maximum voltage will be 6,336 volts. All right. So that is the volt per division that you're given times the length that you're given to the maximum, which is 1,32. And the other part was to calculate the peak to peak. So in this case, yes, we can use the number of dev times this, but peak to peak, guys, the moment I have the peak voltage, I can calculate peak to peak. Remember, we talked about this part of peak to peak just being 2 times what? The peak voltage or the maximum voltage. I can simply use this formula, 6,336 volts. So this is going to give us something like 12,762 volts. All right, so that's the peak to peak voltage. So these are the typical questions that we might be given. This is our exam. This is our August 2023 exam, and it's just important that we talk about these. Yes, as we are revising the theory and so on, I encourage you to revise your theory. As you can see now, to say, okay, these are the typical questions that I might be given. Now it enables you to be revising your theory also. So it's good to know the layout of the paper that you're going to have at the end. Know your typical questions. How am I going to be able to answer these typical questions? Then apply the information that you are given, or now that you know that your syllabus, it covers up to this, revise up to those, whatever that is giving you a challenge now, make sure that you revise that topic. You can see, okay, this topic is still having some challenges or some drawbacks. Work on that. That is the idea. So that was the full paper, guys. Do not forget to share our platform to our friends, and also just become a member so that you support us as much as you can, guys, so that we can be able to reach others and also to create this part for others to come. We just need to work on more and more and more each and every day. So if you become a member, it helps us a lot. It helps us to put up everything, all the resources needed, so that we can reach out others. That is, guys, that's it. Till we meet again.